Hello and welcome again to my Physical Science online video lecture supplement series. In today's video, I want to work through some of the examples which I have prepared for Chapter 3, which is the Force and Motion chapter of your Physical Science text. So this corresponds to Chapter 3 of the Shipman, Wilson, Higgins, and Torres Physical Science textbook. Before we look at these examples, I want to show a little review of some of the important equations in this chapter. There's sort of quite a few in this particular chapter. These are, of course, listed in your physical science text as well at the end of the chapter, after some of the early homework questions, but before you do the exercises at the end of your chapter. There's usually an important equations section, and these are the equations that found their way into that section. So without further ado, let's look at some of the examples. A block of mass 0.5 kilograms is pulled with a total unbalanced force of 2.5 newtons. What will be the block's acceleration? To answer this question, we use Newton's second law of motion, which you can find in the notes. That's the one that says that the acceleration is proportional to force over mass. Usually it's stated as F equals ma, but of course the thing that we're asked to solve in this particular problem is the acceleration. So this is the formulation we might want, and in fact we can just write acceleration equals force over mass, as is done down here, A equals F over m. Alright, so we're basically using the mass of the block m and the unbalanced force F to find the acceleration A. So A is equal to F over m, so that's 2.5 newtons per 0.50 kilograms. And remember, with unit analysis, that a newton you can also write as a kilogram meter per second squared. And so our kilograms on top and our kilograms on bottom should cancel. And so your acceleration should be 2.5 divided by 0.5. And so if you need to, you can use a calculator to solve this at this point. It's just plugging in numbers. 2.5 divided by 0.5 should give us 5. And if we want to record with the right number of significant figures, you notice that there's 2 significant figures and 2 significant figures here, so we would put 5.0 meters per second squared, and that is in fact what the acceleration of this block is going to be. What net force do we need to accelerate an 8 kilogram block by 9.8 meters per second squared? To solve this problem, we need to use Newton's second law of motion, which says that the net unbalanced force should be equal to the object's mass times the acceleration caused by that net unbalanced force. So force equals mass times acceleration. So we're going to use F equals ma, where this right here represents F, the net force. This right here, acceleration, is 9.8 meters per second squared. That's going to be A. This right here is actually the mass of the block, m. So we would write F is equal to 8.0 kilograms times 9.80 meters per second squared. So that's going to give us F equals, let's use our calculator just to be safe, 8 times 9.8 gives us 78.4. So this is 78.4 kilogram times meters per second squared. And this unit, kilogram meters per second squared, is the same thing as the unit newtons. So our force is 78.4 newtons. And of course, we should round to the correct number of significant figures. Since this was 8.0 kilograms, the correct number of significant figures is 2, because there's 2 here and 3 here. So that means that our total force is actually going to be recorded as 78 newtons. And it's worth noting that this force that we found is actually also equal to the weight of the object. And the reason why it is the weight of the object is because this 9.80 meters per second squared acceleration is the free fall or gravitational acceleration near the Earth's surface. So what that means is that if you have an object which is near the Earth's surface and you were to release that object so that it was in free fall, then the force of gravity from the Earth acting upon the object would give that object an acceleration of 9.8 meters per second squared. Hence, this force that we found, 78 newtons, is the weight of this 8.0 kilogram block, because the weight is just another way of saying the force of gravity applied by the planet, in this case by the Earth. Suppose we're given the amount of force and the acceleration caused by that force. Can we use that to find the object's mass? To do this, we can use Newton's second law of motion. That's the one that says acceleration is force over mass, or force equals mass times acceleration, again. And the thing that we're looking for is the mass of the object. So we're basically given the force F and the acceleration A. So we need to solve one of these two equations for M, and both of them will have the same solution for M, because these two equations are the same equation that's been rearranged. So we can write F equals MA. Again, this right here, 30 newtons, is the force. This right here, 5.0 meters per second squared, is the acceleration. And what we're looking for is the mass, which is represented by the letter M. So if we solve this one for M, we would have F over A is equal to M, which is the same as saying that M is F over A. So now we can plug in the numbers, 30 newtons divided by 5.0 meters per second squared. So 30 divided by 5 is 6. So this would be 6. And assuming that the 0 on the 30 is significant, this would be 6.0 kilograms. Just for fun, let's do it the other way too. The other way said that A is equal to F over M. So we can multiply both sides by M, and we would get MA is equal to F. Then we can divide both sides by A. So over A, cancels the A's on this side, and you're left with M equals F over A. So again, that's 30 newtons divided by 5.0 meters per second squared. And again, that's 6.0 kilograms. So you see that these two equations that I have are different ways of stating the same Newton's law. Therefore, the object's mass in this case should be 6.0 kilograms. There is an example from your textbook which has two masses that are basically tied together by a string, and a force of 8.0 newtons pulls to the right on one of the masses, and a force of 5.0 newtons pulls to the left on the other mass. And the question is, what is the acceleration of this system? All right, in order to do this, we have to basically rewrite Newton's second law. And it's basically, you can write it as that the sum of forces, this character is called a sigma, means sum of. That's another way of saying take all the forces and add them together. Should be the mass of everything in the system, so we'll call that m system times the acceleration of the system. And in this case, the system is this pair of blocks which are tied together. Since they're tied together, they should actually have the same total acceleration. The diagram actually shows that the acceleration is this way. So the mass of the system would be 1 kilogram plus 1 kilogram, or m1 plus m2. And the acceleration of the system is called a in this diagram. The sum of forces part, though, what we do is we literally take each force that's on the system and add them together. So that's going to be F1 plus F2. So F1 is minus 5.0 newtons. F2 is plus 8.0 newtons. And so this total force is basically 8 minus 5, or 3.0 newtons. So 3.0 newtons is equal to this acceleration times this total mass. So the total mass, again, is 1.0 kilograms plus 1.0 kilograms. And we're getting that because each of these two is 1 kilogram. So that's the same as 2.0 kilograms in this case. All right, so we can set 2.0 kilograms times the acceleration equal to 3.0 newtons. And that means that the acceleration should be 3.0 newtons divided by 2.0 kilograms. And so 3 divided by 2 is 1.5. So this should be 1.5 meters per second squared. So now we have the answer for what is the acceleration of this system. It is 1.5 meters per second. In that previous problem that I just worked, the immediate follow-up question would be, what is the net force that acts on each one of these two blocks that are accelerating? Well, we can apply Newton's second law to each block individually. So you have one system that's just block number 2, you have one system that's just block number 1. And let's look at those in turn. So for block number 1, we would have net force on 1 is equal to mass of 1 times acceleration of 1. So let's call this NET1 for net 1. And basically we're solving for this guy because we're looking for the net force on each block. So we'll call this F net 1 or 2. So this would be F net 1 is equal to 1.0 kilogram times 1.5 meters per second squared. So now F net 1 must be 1 times 1.5, or 1.5 newtons. So F net 1 is 1.5 newtons. Okay, let's look at block number 2. For block number 2, we would have F net 2 is mass 2 times acceleration 2. So that's going to be 1.0 kilograms again, because block number 2 had a mass of 1.0 kilograms, times 1.5 meters per second squared. And this is because both blocks are accelerating together, they're going to have the same acceleration. So F net 2 is going to be equal to 1.5 newtons. So in this case, both blocks have the same net force acting upon them. I should note here that that's not true for all cases. If we applied the same forces to these two blocks, but they had different masses, we would get a different net force. Or let's say that we applied a different amount of force to these two blocks such that they still have a 1.5 meter per second squared acceleration, but one of the blocks is more massive than the other. In that case, we would also not have the same force applied to each block in net. For example, suppose this block was actually twice as heavy. So instead of 1 kilogram, what if it was 2 kilograms? Well, then instead of having 1.0 kilogram here, we would have F net 2 is equal to 2.0 kilograms times whatever the acceleration of the system is. Let's say, for the sake of argument, that we apply a different amount of force here and here so that the acceleration stays 1.5. Then you'd have 2 kilograms times 1.5 meters per second squared, and that would be 3.0 newtons. This one would be unchanged because the mass is unchanged and the acceleration is unchanged. So this actually kind of begs the question, how much force would we need to apply to the system to make this happen? There's two ways really of going about solving this. One is that you can leave this force alone and just change this one. The other is that you can change both together. And the third, I guess, would be to change this force but not change this one. So the net force for the system in this case would need to be F net system, so I'll just put an S for system, is mass of system times acceleration of system. And the mass of the system would now be 1 kilogram plus 2 kilograms. So that would be 3 kilograms times 1.5 meters per second squared. So 3 times 1.5 would be 4.5. And then the unit is newtons. So how would you get 4.5 newtons? Well, one way of doing it would be to change this from 8 to 9.5 newtons. Then you'd have 9.5 minus 5 is 4.5. Another way of doing it would have been to leave this alone and keep it as 8 newtons, but reduce this guy from 5 down to only 3.5. Then you would still have a force of 4.5 because you'd have 8 minus 3.5. Finally, there's also the possibility of changing both forces so that they're proportionate. And the way that you do that is you could try multiplying both of these numbers by a common factor. For example, to keep this acceleration, I might multiply this by 1.5, so times 1.5, and this would become 12 newtons. And I might multiply this by 1.5, so you'd have 5 newtons times 1.5, which would give us 7.5 newtons. And if you subtract 7.5 minus 12, 12 minus 7.5, you end up with 4.5 newtons. So any of those ways will give you the correct amount of force in order to make this happen. In any case, if we leave these two masses at 1 kilogram each and we leave these two forces at 8 newtons and 5 newtons respectively, then each of these two blocks will have a net force of 1.5 newtons acting upon it. And in fact, it'll be 1.5 newtons from left to right. So what is the force of tension in the string between these two blocks? Again, we've already basically solved for the acceleration of the two blocks. We've already solved for the net force of the two blocks. We can use that information to get the force of tension in the string. All right, well, in the previous problems, we already solved that the acceleration is 1.5 meters per second squared, and that the net force on 1, which is equal to the net force on 2, is 1.5 newtons for this case. So the question is, how much force of tension is there in the string? Well, you've got two options here. What the force of tension does, by the way, is it basically tries to pull the string back together. So it means that there is a tension force right here, and it means that there is a tension force right here. And we're going to go ahead and call these T2 and T1. And it turns out that T2 and T1 should be equal. Now, let's see why that is. So let's look just at block 1. So block 1 has the condition that says that the sum of forces on block 1, that's the very definition of net force, is equal to 1.5 newtons. But the sum of forces must be equal to the first force, which is labeled F1, plus the second force, which is T1. So this means, if you combine all this information, it means that T1 should be whatever the net force is minus the force F1. Now, force F1 is to the left. That means that there should be a negative sign introduced to it. So T1, according to this, is going to be 1.5 newtons minus negative 5.0 newtons. And so that would be 6.5 newtons. All right. We can double check that, by the way, by noting that the net force should be the mass times the acceleration. So that means that T1 plus F1 should be mass 1 times the acceleration. And so T1 should be mass number 1 times the acceleration minus F1. And so this again becomes T1 equals 1.0 kilogram times the acceleration is 1.5 meters per second squared minus a negative 5.0 newtons. This right here is 1 times 1.5, so that's 1.5 newtons. Minus a negative 5 is the same as plus 5, so that is 6.5 newtons. So we've come up with the same answer both ways for T1. Now let's look at block number 2. So block number 2 has the same basic conditions, namely sum of forces on block 2 is, by very definition, the net force on block 2, and that's found previously as 1.5 newtons. So we have 1.5 newtons, and then furthermore, block number 2, the sum of forces on block 2 must be this force plus this force. So that's F2 plus T2. So this means that T2 should be F net 2, setting this equal to this, minus F2. So T2 should be 8.0 newtons. Should be negative 8.0 newtons plus 1.5 newtons. I'm afraid that I've switched the order of these two around. And so that means that T2 should be 6.5 newtons. And if we did it using Newton's second law, F equals ma, we'd come up with the same answer. This, of course, is a negative number because it is pulling to the left. This one was positive because it's pulling to the right. Usually when we ask what is the force of tension in the string, we simply mean what's the magnitude. So the magnitude is sort of the absolute value, and you notice that it's 6.5 for all of these. So we would say the string's tension must be 6.5 newtons. So now the question is, suppose we double both masses. How do the answers to these previous set of examples change if we do that? All right, so this is a relatively long example compared to the others because it's basically asking us to go duplicate all the work that we've just done. But this also should serve as a nice double check that you follow what it is that we've done so far. So we start off by saying that the sum of forces for the system is equal to the mass of the system times the acceleration of the system. And the system in this case we're going to define to be this pair of blocks taken together. All right, so that means that the mass of the system is the mass of block 1 plus the mass of block 2, which is 2.0 kilograms plus 2.0 kilograms, or 4.0 kilograms. The forces acting on the system are force number 2 and force number 1, which act in opposite directions. So we can introduce a minus sign here to represent that. So sum of forces on the system should be F1 plus F2, and that's negative 5.0 newtons plus 8.0 newtons, or 3.0 newtons total. So we have the same net force on the whole system. Okay, what that means is that the acceleration for the system we can write as a system, which we often just represent with an A, is going to be sum of forces on the system divided by the mass of the system. Okay, so the acceleration for the system, according to that, is going to be 3.0 newtons divided by 4.0 kilograms. So at this point, you either mentally calculate this or you throw it into your calculator, and what you get is 0.75 meters per second squared, which actually is half of the acceleration that we found before. So the acceleration is half as much. What do you think that's going to do to the net force on each block? Well, the acceleration is half as much, the mass is twice as much. That means that the net force, we'll call this FB2, would be mass 2 times acceleration of 2. That's going to be 2.0 kilograms times 0.75 meters per second squared. Multiply those two together and you get that the net force on block number 2 is 1.5 newtons. And you're going to find that the same thing is true for block number 1. Force net for block number 1 is mass 1, acceleration 1. So that is going to be 2.0 kilograms times, again, 0.75 meters per second squared. So we should get the same number. Force on block 1 is 1.5 newtons. So the net force in both cases is 1.5 newtons. Finally, the question is how much tension is there? So notice that this net force is the same as before, which makes sense because the two forces are the same as before. So what about tension? Well, we can use basically that tension 1, now we're using only the isolated system of block number 1. So tension number 1 should be equal to the mass times the acceleration of block 1, m1, a1, minus f1. Or we could use T1 is equal to FB1 minus F1. All right. Either way, what we're going to find is that tension 1, so this right here would be 1.5 newtons minus negative 5 newtons. So that is 6.5 newtons. So it's same as before. And ditto is going to be true for T number 2. So therefore, to reiterate this result, when we double the two masses, what we end up getting is that the acceleration is half as much as before, but the net force and the string's tension are both unchanged. Again, if we were to change only one of these two masses, but not both, then you could change the acceleration and the tension and the net force on each block. But so long as we change both together by doubling both, the only thing that changes is the acceleration. Now we ask, what is the weight and the normal force that act upon a block that's sitting on a flat level surface given the block's mass? In order to get the weight, we go to this slide from the notes, which says that while the mass is the amount of matter present, the weight is given by the force of gravity acting on an object. So basically, if you're on the Earth, the weight is the mass times the acceleration due to gravity. And a way of applying that is just to say weight is equal to m times g, where g is 9.80 meters per second squared, the free fall acceleration, in other words. And this is a second case of Newton's second law. Newton's second law being F equals ma. So this is saying that the weight should be the mass times the gravitational acceleration. So that's 4.00 kilograms times 9.8 meters per second squared. So we need to multiply 4 times 9.8. So 4 times 9.8 gives us 39.2. So this is going to be 39.2 kilogram meters per second squared is the same as a Newton. So the weight is 39.2 newtons. What about the normal force? We can give an N to represent the normal force. And the way that we can get the normal force is, we notice in this diagram the block is sliding in this way. That means that in the vertical direction there is no acceleration. And if there's no acceleration, then we can write that the sum of forces is equal to 0. That's Newton's first law. So Newton's first law of motion is basically telling us that the normal force needs to counteract gravity when you're in a situation like this. So the normal force should be equal to the weight, but in the opposite direction. And since we just found the weight to be 39.2, that means that the normal force should also be 39.2 newtons. So this 4 kilogram block has a weight of 39.2 newtons. It has a normal force of 39.2 newtons. All right, follow-up question to that last one. The block is now sliding on a surface that has a coefficient of friction of 0.45. So what is the force of friction which is acting on this block if that's the case? So let's give friction a label. I'm going to label it as lowercase f for friction. And the way that we find friction is that we first need to ask what kind of friction we're finding. Are we finding static or kinetic friction? Well, the block is actually moving, so that means that we need to be finding the kinetic friction. That's the friction that occurs when there's relative motion between surfaces in contact. The block is not stationary, but if it were, then we'd be finding static friction. And in order to find friction, what we have to use is the coefficient of friction, which is then multiplied by how hard the two surfaces are being pushed against each other. So what is a measurement of how hard two surfaces are pushed together? Well, that measurement would be called the normal force. So basically, one way of thinking about friction is that it is the force of, shall we say, stickiness, if you will, between two surfaces. It makes the two surfaces not want to rub against each other. And so the harder the two surfaces are pressed together, the harder it is to slide one surface across the other. And the force which measures how hard two surfaces press together is called the normal force. So that means that friction should be equal to the coefficient of friction times the normal force in the case of kinetic friction, or in the case of static friction, it's less than or equal to that coefficient times the normal force. And where this is coming from is basically this coefficient of friction can be thought of as a ratio. Specifically, it's the ratio between how hard two surfaces are pressed together versus how hard it is to move one surface across the other, or one object across the other object, surface to surface. So this is basically a ratio of those two forces. Therefore, to solve this question, we basically can write that friction is equal to mu times the normal force. And again, the block is sliding, so this is actually the kinetic friction that we're finding. So that would be 0.45 times the normal force, which is 39.2 newtons. We found that previously. So this force of friction, therefore, is going to be given by 0.45 times 39.2. So that's 17.64 newtons. So what that means is that you would need 17.64 newtons of force that you're applying to this block in this direction in order to counteract the force of friction pulling in this direction. In other words, if you wanted to make this block move at a constant speed along this surface, you'd need to put a horizontal force of 17.64 newtons on it. And again, this number is going to change depending upon whether you're actually just putting a horizontal force or whether you're putting a force that has a horizontal and a vertical component. If there's a horizontal and a vertical component, then this vertical component may either enhance or detract from the normal force. And so that's going to adjust what the horizontal component is. So the force of friction acting on this block ends up being 18 newtons. And the reason why it's 18 as opposed to 17.64 is because our coefficient of friction only has two significant figures. So we would need to be rounding that off to 18 newtons. Right. So let's look at another question that builds off of these previous couple, which is now we want to know what the acceleration of this block is going to be, assuming that this force diagram is correct. In other words, normal force and gravity are perfectly balanced against each other, and friction acts in the direction opposite that the block is sliding in, but there are no further forces acting upon the block. If this is the case, then this is equivalent to saying that the total force on the block would be friction plus the weight plus the normal force, and the normal force and the weight actually cancel out. And by Newton's second law, that should be the mass times the acceleration. So what this all is saying basically is that the acceleration should be the friction force divided by the mass of the block. Now, the friction force we found in the previous problem was 18 newtons. I'll go ahead and put in the 17.64 newtons that we found before and divide it by 4.00 kilograms, bearing in mind, of course, that we really have two significant figures here because you can always round at the very end of the problem. So we take the 17.64 newtons from the previous one, we divide that by 4, and we end up getting 4.41 meters per second squared. So this right here, 4.41 meters per second squared. And again, we're going to want to round that off to only two significant figures. So we would record this acceleration as 4.4 meters per second squared. Now suppose we have a block whose mass is 5 kilograms and which is sliding along a surface which has a coefficient of friction 0.25. If that's true, can we determine what the block's weight and its acceleration are going to be. Again, this is a flat level surface, so the normal force and gravity are equal in magnitude in opposite directions. So that means that friction is the only unbalanced force remaining to act upon the block. Okay, well, the weight you can find by applying Newton's second law is going to be the block's mass times the free fall acceleration. So the mass m is given right here. The weight is W is what we're trying to find, and G is always 9.8 meters per second squared. So this is 5 kilograms times 9.8 meters per second squared. So if you multiply those two numbers together, what you will find is that the weight is approximately 49.0 newtons. And therefore also the normal force is going to be approximately 49.0 newtons. So now we're looking for what's the acceleration. Well, the acceleration times the mass should be equal to the force of friction. That comes from Newton's second law. So Newton's second law is the one that says that the sum of forces is the mass times the acceleration. And in this case, the sum of forces are going to be given by the normal force plus the weight plus friction. There's a normal force, there's friction, there's the weight, or gravity. And these two are in opposite directions and of equal magnitude, so they go away, and you're left with little f friction is equal to mass times acceleration. That means that the acceleration should be the friction divided by the mass. So how do we get the friction? Well, friction again is going to be obtained by taking the normal force between these two surfaces and multiplying by the coefficient of friction, which is given here. Again, we're assuming that's already in motion, so this is a coefficient of kinetic friction. So the acceleration should be given by the coefficient of kinetic friction times the normal force divided by the mass. So that is 0.250, which is a unitless quantity, times 49.0 newtons, divided by the mass, which was 5.00 kilograms. But notice we don't actually need to put in both of these numbers because this normal force was given by the mass times the free fall acceleration. So we could have just canceled these two masses out and been given that the acceleration is the coefficient of friction times the free fall acceleration, or 0.250 times 9.80 meters per second squared. This is valid if sliding on a flat surface. So if sliding along a flat level surface with friction as the unbalanced force, that is. Which I'll abbreviate as calling it the only force. In any case, if you put in those numbers, let's take the 0.250 number that it represents the coefficient of friction, and now we multiply it by 9.8, and what we come out with is 2.45. So 2.45 meters per second squared. And again, we should notice that there are three significant figures in both, so these are the forms that your answers should end up appearing as. Thus, we write that the weight is 49.0 newtons and the acceleration is 2.45 meters per second squared. Suppose that you have a block of known mass, and it's sliding along a flat level surface in such a way that we're able to measure its speed at a couple of moments in time. The initial speed is 2 meters per second, and then a second later it's only 1 meter per second, and another second after that it has stopped. So we want to know what is the force of friction and the coefficient of friction which act upon this block. Well, the force of friction you get out of Newton's second law. Basically, we use sum of forces is mass times acceleration, and the sum of forces is going to be the weight plus the normal force plus friction. Weight and normal force are going to cancel because it is a flat level surface. So this is saying that the lowercase f friction force is the mass times the acceleration. So the mass we have, it's 5.0 kilograms. So this right here represents the mass m. How do we get the acceleration out of this? Well, we're going to have to go back to an earlier lecture in order to get that. Specifically, we need to go back to the chapter 2, which was the one covering kinematics, or just simply motion, from the physical science textbook. And here we can review what acceleration is. It is the time rate change of velocity. And the way that we calculate acceleration so far is that we take an average acceleration, which is change in velocity per time for the change to occur. So that might be delta v over t, or vf minus v0 over t. So I'm going to shorthand that as acceleration is delta v over delta t. And you'll notice that there is a constant rate of change here. We started at 2, and then in 1 second we went to 1 meter per second. And after 2 seconds we were at 0 meters per second. So regardless of which two of these we use for our delta v and our delta t, we're going to get the same answer. So we'll use 2.0 meters per second, which is our initial speed, minus our final, 0.0 meters per second. And our initial time was 0.0 seconds. And our final time was 2.0 seconds. So final time 2.0 seconds, final speed 0.0 meters, initial speed 2.0 meters per second, 0 seconds. So this is going to give us an average acceleration of negative 1.0 meters per second squared. And notice that that's the same thing we would get if we used, say, 1 meter per second, comma 1 second, 2 meters per second, comma 0. We would have had 1.0 meters per second minus 2.0 meters per second divided by 1.0 seconds minus 0.0 seconds, which is 1 over, or minus 1 meter per second over 1 second. And that's still going to give us 1.0 meters per second squared, and so on. So we now have an answer for the acceleration. We have one for the mass. So the force of friction needs to be mass times acceleration. So that's 5.0 kilograms times 1.0 meters per second squared. And this guy's negative. So the force of friction would be negative 5.0 kilogram meters per second squared, which is the same as negative 5.0 newtons. And then the minus sign is not strictly necessary. You could think of it as being that we've defined this way to be the positive direction, and so the friction is acting in this way, which is the negative direction, and that's where that minus sign has come from. In any case, now we want to figure out what this coefficient of friction is. Again, it's probably going to be a coefficient of kinetic friction. And one way of doing that is by recalling that the magnitude of the force of friction is the coefficient of friction times the normal force. So that means that the coefficient of friction should be the force of friction divided by the normal force, which should be equal to the force of friction divided by the weight, because the normal force and the weight are equal. So that means that we have 5.0 newtons. Again, we're only caring about the magnitude, so this sign doesn't matter. 5.0 newtons divided by 5.0 kilograms times 9.80 meters per second squared. And so this is going to give us a coefficient of friction of, let's do this, 5 divided by 9.8 divided by another 5, and that's 0.102. So I'm just going to write 0.102, and that is a unitless quantity. So we can box that, and now we've got our answer. So with the correct number of significant figures, the friction becomes 5 newtons, the coefficient of friction becomes 0.10, and I've dropped all the minus signs because it's understood that the friction is acting in this direction. Suppose you have two spherical asteroids, like in this picture, only maybe a little more spherical shaped, and the two are separated center to center by 100 meters. And we know the mass of each of them. This is 2 billion and this is 4 billion kilograms. So we want to know what's the gravitational attraction between these two asteroids and what's the acceleration of each towards the other at the initial separation. Now, before I go ahead and calculate the answer to this for you, before I work this example for you, in other words, I wanted to remind those of you watching that this E plus 9, this capital E plus 9, is how you enter scientific notation within a computer context. So 2.00 capital E plus 9 is the same thing as 2.00 times 10 to the power of 9, which is 10 times 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 10, or 1 billion. So let's go ahead and now do this example. To solve this problem, we're going to need to use Newton's law of gravitation, along with actually Newton's second law of motion. And Newton's law of gravitation can be expressed in equation form by F equals big G m1 m2 over r squared, where big G is called the universal gravitation constant. It has a value of 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Yes, that is a mouthful. Yes, you might want to write that down for doing your homework and your tests. The two m's are basically the mass of the two objects which are attracting each other. So in this case, it's the mass of the first asteroid and the mass of the second one. The r squared is the separation distance between them. So as a simplified diagram, here's where asteroid 2 is located, here's where asteroid 1 is located. They both have a force towards each other. That force is given by this equation. They are separated by distance r. Notice that this force and this force have the same magnitude. However, the accelerations are not necessarily going to be the same because this mass and this mass are not equal. So here, therefore, is what this basically looks like summarized in the diagram that shows our two asteroids in question. So here's the middle of the first one, here's the middle of the second one. They are 100 meters apart, I'm afraid I couldn't fit the 100 meters in here. This one is the larger one, has a mass of 4 times 10 to the 9 kilograms. This is the smaller one, 2 times 10 to the 9 kilograms. And again, the equation that we're using is Newton's law of gravitation. So that would be F is equal to big G times M1 times M2 over R squared, and there's usually a negative sign to denote that they're being pulled towards each other. So it doesn't matter which of the two asteroids we pick as the attractor and which one is the attractee. Both experience the same force. That's Newton's third law. Although, if you notice in this equation, choosing one or the other to be the attractor just switches which one has M1 and which one has M2. Either way, you're going to get the same number. So we write F is equal to negative 6.67 times 10 to the minus 11 Newton times meters squared over kilogram squared. So that is the universal gravitational constant. That is times 2 by 10 to the 9 kilograms, 2.00 times 10 to the 9, that is. And then 4.00 times 10 to the 9 kilograms. And then we divide that by the radius squared, which would be 100 meters quantity squared. So now we can use the calculator. So we have 6.67 times 10 to the minus 11. The way you enter that, by the way, is you put in the 11, you make it a minus 11, and then you hit 10 to the x. So now we've entered the first number. Now we need the second number, 2.00 times 10 to the 9th. So we hit 9 and then 10 to the x. So now we're going times 10 to the 9. And now that is going to be times 4.00, and that's times another 10 to the 9. So this number, now we've got to divide that by 100 meters squared. So 100 meters squared. And that gives us 53,360 newtons. So go ahead and write that down, 53,360 newtons. So that's the force of gravity between these two asteroids. The other part was, what is their acceleration towards each other? So to get the answer to that, we can actually use Newton's second law of motion. So Newton's second law of motion states that the force should be the mass times the acceleration. And so therefore the acceleration should be force over mass. So for the smaller one, we'll call the smaller one was M1. So F1 is equal to F2 is equal to F. So we can write even that down here. F1 equals F2 equals F. So we would have F1 is M1 A1. And so that implies that A1 is going to be F1 over M1. So that's 53,360 newtons divided by 2 billion kilograms. 2.00 times 10 to the 9 kilograms. So let's see here. We take this guy and we divide by 2 times 10 to the 9, which is like that. And we come out with this very tiny number. So 0.0002668. So 0.0002668 meters per second squared. For the larger one, we end up using F2 equals M2A2. And so what that means is that the acceleration should be given by F2, the force between the two of them, divided by the mass of this larger one. That's 53,360 newtons divided by 4.00 times 10 to the 9 kilograms. And if you put all that into your calculator, what you end up getting is 0.00001334 meters per second squared, which is actually half of this one. And you should maybe count how many zeros there are to figure out scientific notation. This has 1, 2, 3, 4, 5. So this is actually going to be 2.668 times 10 to the minus 5 and 1.334 times 10 to the minus 5 meters per second squared. And so assuming that this 100 meters that's given here is actually 3 significant figures, that means that the force between the two asteroids should be about 5.34 times 10 to the 4 newtons. That's 53,400 newtons. And the acceleration should be 2.67 times 10 to the minus 5 meters per second squared for the smaller asteroid. So that's going this way. And for the larger one, should be 1.33 times 10 to the minus 5 meters per second going this way. Suppose you see an iceberg sitting in the ocean, and you want to know, you maybe can measure how much or figure out about how much of the iceberg is above the surface of the ocean. So you want to know what percentage of the iceberg is underwater in the ocean. How do you approach that problem? In order to solve this problem, we need to use the concepts of the buoyant force and specifically of Archimedes' principle. And this principle states that if you immerse an object in a fluid, then the object is going to displace some of that fluid, which is going to in turn supply a buoyant force upward on the object. And that buoyant force should be equal to the weight of the volume of fluid displaced. So that means if you displace, say, a liter of water, you put an object that has a volume of a liter underneath the surface of water, you've just displaced a liter's worth of water. And that means that the weight of that liter of water is equal to the buoyant force that is being supplied upward on the object. Now the weight of that water is going to be the mass of the water times the free fall acceleration, g. And if you'll recall from the first set of lecture notes from chapter 1, the volume and the mass are related via density. Density is mass divided by volume. So if you have a 1 liter object that's underwater, that 1 liter object should have a total mass of whatever the density of the object is times a liter. And the amount of water displaced should be the density of the water times a liter. And as you know, water has a density of 1 kilogram per liter. So if you've displaced a liter of water, you've displaced a kilogram of water. And that means that you should have a buoyant force of 1 kilogram times 9.8 meters per second squared, which is 9.8 newtons. So when you have a 1 liter object that you place underwater, you get a buoyant force of 9.8 newtons on the object. So for every liter underwater, multiply it by 9.8 newtons. Now, the way that you figure out for this specific problem of an iceberg, you know that the iceberg is floating on the water. And what that means is that the weight of the iceberg needs to be totally supported by the buoyant force from the water. That's Newton's first law in application. The sum of forces on the iceberg must be 0. The iceberg still has weight, Therefore, there has to be some upward force to keep it floating. That upward force needs to be the buoyant force. So if you were to basically synthesize these different principles together, what you end up getting is that the weight of the iceberg needs to be equal to the buoyant force of the water. And that means that the weight of the iceberg is going to be equal to the weight of the water that has been displaced. So now we can apply a little bit of math to this. A floating object in general is going to displace its own weight worth of the fluid. Since the density is mass over volume, we can figure out how much of an object is submerged in a fluid, generally in a liquid, upon which the object is floating, because the mass of the object needs to be equal to the mass of the fluid which has been displaced. And that means that the density of the object times the volume of the object needs to be equal to the density of the fluid times the volume of the fluid displaced. What this implies is that we can get a ratio of the volume of the object to the volume of the fluid displaced. And the volume of the fluid displaced is also going to be the same as the volume of the object which is submerged. All right, so the submerged volume is going to be the ratio of the object density over the fluid density times the volume of the object. Okay, backing that up a step, we can basically write that rho is mass over volume, and we need mass of object to be mass of fluid displaced. So this right here is basically mass must be rho times volume. This one right here, therefore, is implying that the density of the object times the volume of the object, that's the mass of the object, should be equal to the density of the fluid, which has been displaced, times the volume of the fluid, which has been displaced. And the volume of the fluid which has been displaced is also equal to the volume of the object which is submerged. So in the case of this iceberg, this whole volume is the iceberg volume. And if we were to sort of draw a line representing the part that is underwater, that's basically this part that I'm more or less circling here. This right here would be the volume submerged, and that's also going to be equal to the volume of the displaced water. All right, now the other thing that you have to do, and this is what makes this problem a little more complicated than the ones that we have done so far, is that we're asking what percentage of the iceberg is underwater. Now, one way of doing that is to note that the percentage is the submerged volume divided by the total volume times 100%. That's just how you find the percentage. And since the submerged volume is equal to the volume of the fluid displaced, we can also say that this is volume of fluid displaced over volume of object, because the total volume is just another word for the volume of the object, times 100%. So looking up here, I notice that we can get an equation that looks like that from just these. So if you have rho object times V object, and that's equal to rho of the fluid displaced, the density of the fluid displaced, times the volume of the fluid displaced. And you want the volume of the fluid displaced over the volume of the object. Then you should divide both sides by the volume of the object. All right, so this right here gives us that the density of the object is equal to the fluid density times this ratio that we're wanting, fluid density over object, fluid volume over object volume. So now we need to divide both sides by the fluid density. All right, so that gets rid of this. And what you're left with is volume of fluid displaced over volume of object is equal to density of object over density of the displaced fluid. All right, so that times 100% gets us the thing that we're looking for. So in the context of this actual problem, that means that the submerged part of the iceberg divided by the total volume of the iceberg times 100% should be the density of the iceberg, that would be this number right here, divided by the density of the salt water, which would be this number right here. So we basically write the ratio of the submerged to the total times 100% should be equal to 917 kilograms per meter cubed divided by 1025 kilograms per meter cubed. And that's times 100% if we want to get a percentage. So out comes the calculator. So 917 divided by 1025 gives you 0.894, and then that times 100 should give you 89.4. So 89.46% is submerged. So this is roughly 89.46%. And so given that we have only 3 significant figures for this density, that means 89.5% of the iceberg will be underwater. Certainly lets you see what's meant when people say just the tip of the iceberg. We're only seeing the top 10% of this iceberg, and the other almost 90% is underwater. Now suppose that you have a chunk of aluminum. So the density of aluminum is known, and maybe we know that it's a 100 kilogram block of aluminum. And it's initially suspended underwater and then released, and it's in fresh water. And what we want to know is, what's the magnitude of the buoyant force on this block of aluminum? And for that matter, is this aluminum going to float or sink when this buoyant force is applied? If you place an object inside of a fluid, in other words, you totally submerge the object, then the object is going to displace its own volume worth of the fluid. That's true whether the object is lighter than the fluid or heavier than the fluid or what. And basically what happens is that this means if you take the volume of the object and you multiply it by the density of the fluid, you get the mass of the fluid which is displaced. And you multiply that by g, and you've got the weight of the fluid displaced. And if that weight, which provides the upward buoyant force, if that weight is greater than the object's weight, then the buoyant force is going to push the object up to the surface. If the weight is less than the object's weight, if that buoyant force is smaller than the object's weight, then the object's going to sink. There's not enough force to suspend it where it is being held. And so the object is going to start basically sinking. So what we can do is figure out, given the data we've been given, how much weight of fluid is this block of aluminum displacing, and is that weight enough to balance the aluminum so that it does not sink? All right, so we submerge our aluminum block. That means that the volume of the fluid displaced is equal to the volume of the block. Okay, the volume of the block is going to be given by the fact that we know what the mass of the block is. This would be m of object, or m of block. Or we could say mass of aluminum, Al. So the density of aluminum is also given. This would be density of aluminum. And density is always going to be mass over volume. So that means that the volume should be the mass divided by the density. So we can have the mass of the aluminum and the density of the aluminum. So that is in turn going to be equal to the volume of the fluid which is displaced, the water, in other words. All right, well, how much force does that volume of water have? Well, the mass of the water is what we're looking for to get that buoyant force. The buoyant force is going to be the mass of the fluid displaced times g. And since rho is m over v, we can also write that the mass is the density times the volume. That's just rearranging this equation here. Okay, so this right here is now telling us that the density of the displaced fluid times the volume of the displaced fluid times the free fall acceleration is the buoyant force. All right, well, now we can substitute for this. This is given by 1,000 kilograms per meter cubed. So this is rho of fluid displaced. This term right here is the term that we can make a substitution for because the volume of the fluid is also equal to the volume of the block, which is going to be equal to the mass of the block divided by the density of the block. And of course, the gravitational acceleration would be 9.80 meters per second squared. So let's put all that together, and what we get is that the buoyant force should be the density of the fluid, which is being displaced, times the mass of the aluminum block divided by the density of the aluminum block, times the gravitational acceleration. So this gives us 1,000 kilograms per meter cubed times 100 kilograms times 9.8 meters per second squared divided by 2,700 kilograms per meter cubed. And if you want to check units, you'll notice there's a kilograms here, there's a kilograms here, there's a per meter cubed here, there's a per meter cubed here. So we're left with kilograms, meters per second squared. That gives us newtons, so that's good. So basically at this point, we may want to use our calculator, and you have 1,000 times 100, so 100,000, times 9.8, so 980,000, divided by 2,700. And what you're left with is 362.962. So the buoyant force is going to be equal to 362.962, repeating actually, newtons. All right, so is this thing going to float or sink? Well, one way of checking that is that we can look at this density ratio. And it turns out that the fraction of the weight of this block that this buoyant force is going to supply is going to be equal to this density ratio. So the buoyant force divided by the actual weight of the aluminum, we'll call that WAL, is going to be this ratio of densities. Density of aluminum, density of the water, which is 1,000 divided by 2,700. The units are the same for top and for bottom. So the units will in fact cancel out. And if you take 1,000 and you divide it by 2,700, what you end up getting is about 37%, 37.037. That's if you multiply by 100%, that is. So 37.04%. All right, so this means it sinks. And if we round off to 3 significant figures, because I'm assuming that this has 3 significant figures, this has at least 3, this has at least 3, then this means that the buoyant force should be 363 newtons. That's still 37% of the actual weight of this aluminum block. Suppose that you have a large boulder, maybe 150 kilograms. That's actually a bit smaller than this boulder would be. And it's moving with a speed of 8 meters per second. What we want to know is, what is the magnitude of the linear momentum of that boulder? To solve this problem, we would look at the section in your notes or your book that's titled Momentum, and specifically linear momentum. And you'll notice that momentum is given by mass times velocity. So you can find the magnitude of the momentum by the mass times the object's speed. And in this case, we don't have a system of masses. The only thing that we care about is this boulder that's moving. So we just use this equation, momentum equals mass times speed. All right, so momentum is P. The mass right here is 150 kilograms, and the speed is 8 meters per second squared. So momentum is given by the mass times the speed, so that's going to be 150 kilograms times 8 meters per second. There's 4 sig figs here, but only 3 here, so we're going to end up with 3 significant figures by the time we calculate all this. So the magnitude of the momentum basically means how much momentum does it have is going to be 8 times 150, that's 1200. So 1200 kilogram meters per second, which is also the same thing as 1200 Newton seconds, where the first zero but not the second zero would be a significant figure in this answer. Suppose that this boulder then crashes into a second boulder. The second boulder is initially at rest but is larger than the first boulder. So after this collision occurs, the first boulder is stopped. So let's assume that nothing silly happens, like the boulder's breaking or that they slow down because of friction or that they're moving up a hill or anything like that. Just assume that maybe they're flat, level ground. First boulder collides with the second one. What will be the speed of the second boulder after that first boulder has stopped? To answer this question, we use what's called the law of the conservation of linear momentum. And what that law basically is, it's our first conservation law so far in physics. And what it is that the total linear momentum of an isolated system is going to remain constant, provided that there's no external unbalanced forces. And this problem has qualified that there are not any external unbalanced forces that act on the system. So that means that the initial momentum of the system, meaning the momentum of the first boulder plus the momentum of the second boulder before the collision, has to be equal to the momentum of the system finally, meaning the momentum of the first boulder plus the momentum of the second boulder after the collision. So that can be summarized by saying that initial momentum equals final momentum. It's not an equals 0 in this case because we have a boulder that's initially moving and one that's initially stationary, as opposed to in your notes where there's a man jumping off of a boat where both were initially stationary. The man jumps, gains some momentum, the boat has to gain momentum in the opposite direction to make both cancel. In this case, we have a boulder which initially has momentum and it's colliding with a second boulder, which initially has no momentum because it's at rest. In any case, we can write that P initial is P final, and what that basically implies is that the mass of the first boulder times the initial velocity of the first boulder plus the mass of the second boulder times the initial velocity of the second boulder should be equal to the mass of the first times the final velocity of the first plus the mass of the second times the final velocity of the second. All right, so now we go and we read some things here. So this right here, 300 kilograms, is representing the mass of boulder 2. Mass of boulder 1 is 150 kilograms. That was given in the previous problem. So that's given in previous problem. And initially, our first boulder is at rest. That means that our second boulder is at rest. V2 initial is 0. So that means that we can get rid of this term because this is 0. After the collision, the first boulder is stationary. This means that V final for boulder number 1 is also 0. So we're rid of ourselves of this term. The initial speed, V1 initial, was 8 meters per second. That was also given previously. So review the previous problem to see where those two numbers have come from. So in any case, this term and this term should be equal, and the thing that we want is the final speed of the second boulder. So that is V2F. So we're solving this equation for V2F. Well, we have M2 V2F is M1 V1I. So final speed of the second boulder times mass of the second is initial speed of the first times mass of the first. So we can divide both sides by M2. And so we're left with V2F, the thing we're looking for. And that is going to be 150.0 kilograms divided by 300 kilograms, because those are the two masses, times 8 meters per second. Well, 150 divided by 300 is a half, and of course the kilograms cancel. So this is a half times 8, which is 4. So the final speed of the second boulder should be 4.00 meters per second. And this is the speed that it has after the first boulder has collided with it. So basically, the first boulder has given all of its momentum to the second boulder in this problem. Now, we're going to eventually cover a second topic called energy. And that's actually going to be in the next set of lectures, which corresponds to the next chapter from your textbook. And when we get there, you can come back to this example if you'd like, and you can calculate what the energy at the beginning is and what the energy at the end is, and see if the energy is conserved. Suppose that you have a wrench, and you pull upon the wrench to apply some force upon it. And that force is 300 newtons, and you pull at an angle of 70 degrees, which is fairly close to what this is. You know, you have to pull maybe a little more of an angle to get to 70 degrees. If you were to pull straight this way, it'd be 90 degrees. So this right here, if this is 20 degrees, then it counts actually as being almost a 70-degree angle. The question is, how much torque is going to act on this wrench? So to solve this problem, we need to know something about torque. And you could think of torque basically as a twisting effect that's being caused by a force that's being applied some distance away from your axis of rotation, or by some set of forces. And torque actually ties into another concept called angular momentum that we'll look at in another example. Basically, what it does is it changes angular momentum if you have an unbalanced torque. Now, here's a nice diagram that sort of shows what's going on with torque. If you grip a steering wheel and you turn the steering wheel by moving your hand up and moving your other hand down, the steering wheel twists and you've applied a net torque to the steering wheel. Typically, you apply some force some distance away from your axis of rotation, and that's how you get your torque. It's basically a force times a distance times an angle between these two vectors. That's why, for example, it's easier to use a wrench to loosen or tighten a fairly tight bolt than it is to do by hand. It's because the wrench provides you with a very long lever arm. If you had a small wrench, for example, you could go take a metal pipe and stick it over the end of the wrench, and that lengthens the arm quite a bit, and then you can get more torque for the same amount of force. So it's a little trick for how to tighten or usually how to loosen an overly tight bolt. So the basic elements that you need in order to get torque are the distance r, the force F, and the angle between the lever arm and the actual force that's being applied. And so torque is Rf sine theta. That's the equation for torque. So in terms of this diagram that's shown here, this right here is our pivot point, and so this right here, this line here, would be the R vector. Here's the F vector. This angle between them is our theta, as shown in the diagram. This right here you could take as being the perpendicular direction. So this angle phi right here is going to be 90 degrees minus theta. So if we're applying a 70-degree angle here, this would be 20 degrees. In any case, we had that the torque was the distance, which is r, or sometimes L, times the force times the sine of the angle between this and this. So you could think of this force vector as being paralleled up here, and this angle right here is also theta, for what that's worth. In any case, the torque in this case will be 0.250 meters. This right here would be the R term. Here is the force term, F. So it's that times 300 newtons times the sine of 70.0 degrees. So this means that our torque can be found using this calculator as 0.25 times 300 times the sine of 70, which I have to enter by putting 70 and then clicking the sine button. 70.477. So 70.477, and the unit for that would be newtons times meters, Newton meters. So that is how much torque is being applied to the wrench. So we should probably round that off to 3 significant figures, assuming that this 300, all the zeros are significant. Then it's 70.5 Newton meters. All right, so you have a tether ball and a roughly massless string. That's another way of saying that the string is very, very light compared to the mass of the ball. And the tether ball is swinging around this pole at a speed of 5 meters per second, and its distance is 3 meters. So we want to know, what is the angular momentum? The angular momentum we usually represent by an L. And it's given by the mass of the object times the velocity of the object times the distance from axis of rotation, if you will. Center of motion is another way of putting that. Now, the angular momentum actually is also a vector, and it is the vector which is perpendicular to both the velocity vector and this radial vector. So typically speaking, you'll have the velocity and the radius in some particular plane, and they will be at least not parallel to each other. And so the angular momentum will either be sticking out of that plane or going into that plane. And you use what's called the right-hand rule to figure out which it will be. So for example, this is a planet going around the sun. It makes an elliptical orbit with the sun sitting at its one of the foci of the ellipse. The two focal points of an ellipse you can think of if you wanted to draw the ellipse that this planet is going around on a piece of paper. You'd put a piece of paper down, you'd stick one push pin here, you'd stick another push pin at the other focal point. You'd tie a string around it so that when the string is taut with this and with this, the end of the string is here. You'd place your pin down and you'd basically draw the figure you can by pulling the string taut in an orbit around the two pins, and you'd get this ellipse. So the sun in this case is basically the axis of rotation for the planet that's in this orbit. And if you wanted to find the angular momentum, here is the velocity vector. It's pointing, for example, upward at this point and downward at this point. These are the aphelion and perihelion of the orbit, if you will. The radial vector points from the center out to where the planet is. So this radial vector would be from here to here, and the arrow would be to the right. This one would be an arrow to the left, and it goes from the sun to this planet. And if you wanted to figure out what the direction of the angular momentum is, you can basically hold your hand with your index finger pointing straight ahead and your middle finger pointing towards the inside, basically perpendicular to that index finger. And then you move your hand, you rotate it until your index finger points along the radial direction. And if you can stick your hand at the center and it's pointing in the direction of the radius and your other finger is pointing in the same direction as the velocity vector, then your thumb is pointing in the direction of the angular momentum if you're sticking your thumb up. So in this one right here, this picture, the planet's going counterclockwise. It turns out that your thumb would be sticking up out of the page. If the planet were to go clockwise, then your thumb would be pointing into the page. And that gives you the direction of the angular momentum. So the angular momentum is pointing out of the page here. If the planet were to move clockwise, it would be pointing into the page. So let's go back to that tether ball and determine what the magnitude of the angular momentum is. And then if we want, we can also figure out the direction, but we need to know which way this ball is moving around the pole. So before we do that, let's label stuff. So this right here would be the radial direction. The velocity vector in this case is actually pointing straight out of the page. So we would basically usually represent that as a circle with a dot in it. For what it's worth, if you want it to point into the page, you'd represent it like this. So from above, that might look like this. Here's the R, and that is 3.0 meters. Here is our flagpole, and then here is our ball. And right now the ball is moving here with a velocity of 5 meters per second. And these two are, of course, perpendicular to each other. The angular momentum, therefore, is the mass of the ball times the speed of the ball times the distance. So here's the mass, 2 kilograms. Here is the distance, 3 meters. Here is the speed, 5 meters per second. So this is 2.0 kilograms times 5.0 meters per second times 3.0 meters. So 2 times 5 is 10, times 3 is 30. So the angular momentum is 30, and the units are kilogram meters squared per second. So kilogram meters squared per second, which is sometimes also called a joule times a second. And we'll learn more about what this unit joule represents in the next lecture, which will cover energy. So this actually answers the question of what is the magnitude of the angular acceleration. We could also ask what is the direction. So if I'm looking down at this pole, I see that the ball is basically moving around the pole in this direction. So I'm looking down from the top and the ball is moving in this direction. According to the right-hand rule, this is the counterclockwise direction, and so that means that the angular momentum vector from this view would actually be upward. From this side view, that means that the angular momentum vector is actually in this direction, L. So the little arrow just means it's a vector. So L is straight up in direction, and it has a magnitude of 30 joule seconds. So again, the ball's angular momentum is 30 joule seconds. The direction would be up, which is the same thing as counterclockwise, assuming, of course, that this ball is actually winding itself around the pole. If it's unwinding, then the direction would be down or clockwise. Okay, the follow-up question to that is, suppose this ball moves around the pole in such a way that it is only 1 meter from the pole. So I guess that answers the previous question. Is it winding or unwinding? It's winding. How fast is the ball going to be moving at that point in time, assuming that there's no friction involved? To answer this question, we use what's called the law of conservation of angular momentum. This law basically states that if you have some object and you don't apply any torque to the object, any unbalanced torque, then that means that the object will have a constant amount of angular momentum. So for example, in this planet going around the sun example, there's no torque applied to this planet. The entire force is always towards the sun, so this direction. And what that basically means is that this planet can speed up as it gets closer to the sun and then slow down again as it goes farther away from the sun. So the force that acts on this planet is always towards the center of the motion, towards the axis of rotation. And that means it does not supply any torque, because that means that the force is always parallel to the radius. So that means that the angle between force and radius is 0 degrees, and sine of 0 degrees gives you 0. So that means that the initial and final angular momentum are being conserved. Since angular momentum is mass times velocity times this radial distance, and since the mass of the planet doesn't change as it gets closer or farther from the sun, that means that as the radial distance shrinks, the speed and therefore the velocity must increase. And the broader way of expressing this is to say that m1 v1 r1 is m2 v2 r2. So for a single object, the mass times the speed times the distance should be equal to the mass times the speed times the distance at some other point in the object's motion. So basically, the initial angular momentum and the final angular momentum are equal. That means m1 v1 r1 is equal to m2 v2 r2. And the ball does not change in mass. So since it's the same ball, m1 is equal to m2, and that means that these two masses would cancel out, and you just have v1 r1 is equal to v2 r2. Now, in the previous problem, we were given that v1 is equal to 5.0 meters per second, and r1 was equal to 3.0 meters. So that was given previously. And if you look above, you'll notice that R2 is actually given up here as 1.0 meter. So this is R2. So now we're at 1.0 meter. Okay, so we're trying to solve for this term right here. We can do that by rearranging the equation. R2v2 is R1v1. And now we divide both sides by R2. And so V2 should be equal, in this case, to R1 over R2 times V1. So that would be 1.0 meters, that would be 3.0 meters divided by 1.0 meters times 5.0 meters per second. And so 3 over 1 is 3. That times 5 is 15. And the units meters would cancel here. So that means that when the ball is 1 meter away from the pole, assuming no friction, its speed should be 15 meters per second. So that's all that I have for this lecture and set of examples. I hope that you found these examples helpful, and